Section 10.7, Complex Numbers. Number 1. The square root of 64. Now, as you know, we cannot take the square root of a negative number. So we factorize negative 64 as negative 1 times 64. Then using the product rule for radicals, we break it down into the square root of negative 1 times the square root of 64. And the square root of negative 1 is defined as I, that's the smallest imaginary number, times the square root of 64, which is 8. And we usually write the number coefficient first, just like we would write a to x, we write 8i. Number 2, the square root of negative 17. Now, unlike on the previous slide, 17 is not a perfect square, but we still write it as negative 1 times 17, and we take the square root of negative 1 times the square root of 17 by the product rule for radicals. And the square root of negative 1 is I. And although we cannot square root 17, we can just leave it in the radical sign. That is more accurate than if we square rooted it to get a decimal. So our answer is I times the square root of 17. And in this case, notice we put the I before the radical sign, because if it were after, it could look like it's under the radical symbol. So typically we put it before the radical sign. Number 3, negative square root of 25. Well, here the negative sign is outside the radical sign, so we have a positive radicand, so we can square root the positive radicand. Square root of 25 is 5, and that negative sign is still there, so we have negative 5 as our answer. Number 6, the square root of negative 6 over the square root of 2. Now, one approach is to use the quotient rule for radicals and write the square root of negative 6 over 2. Negative 6 over 2 is negative 3, so we have the square root of negative 3. That square root of negative 1 part is just I, leaving us with the square root of negative 3. So our answer is I times the square root of negative 3. I times the square root of 3. So we want the radicand under the radical sign to be positive. And we took the square root of negative 1 outside and called it I. I is our imaginary number. Number 8. Here we're subtracting two complex numbers. A complex number has a real part and an imaginary part. So our first complex number is 6 plus 9i. And from that we're subtracting a second complex number, 9 minus 7i. Now when you're subtracting, you have to be careful. When there's a plus sign outside parentheses, like in front of the 6 plus 9i, we can safely drop the parentheses. However, the second set of parentheses have a negative sign, so we need to distribute that negative 1. Negative 1 times 9 is negative 9. Negative 1 times negative 7i is plus 7i. So as soon as we remove the parentheses, when there's a negative sign outside, all the terms inside the parentheses change to the opposite sign, because negative means opposite of. Collecting the real parts together and the imaginary parts together, because just like adding like terms, we can only combine like terms. Here we can only combine our real parts with our real parts and then our imaginary parts with our imaginary parts. So 6 minus 9, those are our real parts, is minus 3. And then our imaginary parts are 9i plus 7i, and altogether that's 16 i's. So our answer is a complex number minus 3 plus 16i. Number 10. Minus 10i times minus 5i. Multiplying the numbers together, we have minus 10 times minus 5. That's 50. And I times I is I squared. Now I squared, what's I squared? Let's look to the right to figure out I squared. I is the square root of negative 1. So if we square I to get I squared, we have the square root of negative 1 squared. Well, when we square a square root, we cancel the square root symbol because they're opposite operations. So that leaves us with minus 1. So I squared is minus 1. So back to our problem, we replace the I squared with negative 1, and we have negative 1 times 50 is negative 50. Number 12. Here we have two complex numbers and we're multiplying them. The square root of 5, that's the real part, plus 9i, the imaginary part, times the square root of 5 minus 9i. Now notice those are the same binomials with opposite signs on the second term. So let's see what happens. Using FOIL, where we go first times first times last, last times first, or outer times outer, and then last times last, or the first term times the first term times the second term times the first term, and the second term times the second term. So going in that order, square root of 5 times the square root of 5, that's just squaring a square root again. We're squaring the square root of 5 by going square root of 5 times square root of 5. That gives us 5. It cancels the square root. Okay, then the first times the second. We have the square root of 5 times negative 9i. Well, we write negative 9i times the square root of 5. And the second term times the first term, we have 9i times the square root of 5. But this time it's plus. And then 9i times minus 9i is minus, because we have a positive times a negative. 9 times 9 is 81, and I times I is I squared. Now as you see, the two middle terms are exactly the same with opposite signs, so they cancel because it produces 0. And we're left with 5 minus 81i squared. Now you know from before that I squared is negative 1. So we replace the I squared with negative 1, and we have 5 minus 81 times minus 1. Well, minus 81 times minus 1, it's a negative times a negative, is positive 81. 5 plus 81 is 86. Number 14, 9 divided by I. Now here we're dividing by an imaginary part. We want to get rid of all imaginary parts in the denominator, because remember, that is a form of a root. That's a square root. It's the square root of negative 1 in this case. And just like we rationalize the denominator when we have a square root in the denominator, here we're going to also get rid of the I in the denominator. And we do it in a similar way. We're going to square the I. We're going to square that square root of -1 by going I times I. And since we multiply the denominator by I, we must multiply the numerator by I. Now in the numerator we get 9 times I. In the denominator, you see how the radical sign, the I, the imaginary part, disappears. Because square root of -1 times the square root of -1, that's I squared, and you know that that is -1. 9 divided by -1 is -9. And our answer is -9 times I, -9I. Now, to understand numbers 17 and 18, in which you have to simplify I raised to different powers, you should understand that there is a repeated cycle that occurs after every 4 I's. And this is how the cycle happens. I is the square root of -1, as you know by definition. And you also know now that I squared, being square root of -1 squared, is -1. Now I cubed, one way to find it is to go I squared times I. Because by the product rule that would be I to the 2 plus 1, which is I to the 3rd. Now I squared is -1, so we have -1 times I, so I to the 3rd power is -I. I to the 4th, what you could do to find that is go I squared times I squared. You know that I squared is -1. -1 times -1, that's easy, that's 1. So I to the 4th is 1. Now when we go down to I to the 5th, look what happens. I to the 5th we could rewrite as I to the 3rd times I to the 2nd. We found I to the 3rd, that's -I, times, and you know I squared, you know, is -1. So we have -I times -1. That's positive I. And if you look back up to the top, that's starting the cycle over. And you would find by continuing to get the next I, that the next one, I to the 6th, would be -1, I to the 7th would be -I, and I to the 8th would be 1. And then I to the 9th would circle back to I. So it keeps repeating itself after every 4 I's. And that pattern you see at the top in purple is I, -1, -I, 1. So let's look at number 17. Number 17 wants us to simplify I to the power of 36. Well, let's see how many cycles are in 36. If we divide 36 by 4, we get 9. And there's no remainder. It means it completes that cycle 9 times and starts over. So it starts over with I to the 0. So our remainder becomes our exponent, and we get 1. Anything to the power of 0 is 1. So you see that 1 is right at the end of the cycle. So here it completed the cycle 9 times and landed right at the end where we see 1. Finally, number 18 wants us to simplify I to the power of 11. Well, let's see how many cycles of 4 are in 11. 11 divided by 4 is 8, remainder 3. So our new exponent is 3. So in this case, it cycled through 8 times, but it didn't land at the end of the next cycle. It landed just one short. It landed at I to the power of 3. And I to the power of 3, if you look at the purple, here's the pattern again, that is negative I. So the answer to this problem is negative I.